So I will want you all to do the practices like on at the same time, right? Go through the last topic. So the last topic usually is stretched out quite long. And I will try to get it done. Nice color paper. I will try to, is it rough paper? I'll try to get it done by next week. Okay. So this week is again a bit more on this. So at the same, so what I did with the other two classes was basically go through some of the questions, and then we tried to figure out which topics you're having difficulties with, right? Through the practices. Like for example, if you don't know how to do vectors, you don't know how to do forces, right? Then we'll go on and send you the video for that. If let's say for example, work energy power stumps you, you don't understand what's work done, you don't understand what's GPE and KE, right? Then I'll go through that with you and I'll send you the recording as well. So that's why we're doing practices now. I don't expect you to be ready to do the practices. No one is ever ready, at this time of the year. But this is me trying to catch much earlier on what are the topics that you are having difficulties with, right? And then, like I said, I think I mentioned it in the previous class as well. Once you start asking me for, um, you know, for the resources, I will then send you. Hang on, yeah, right. I will then send you all the, yeah, like the links. I'll start filling this page up with the links, right, for all your recording resources. I didn't want to put it on the WhatsApp because otherwise it'll just flood the thing, right? So you can treat this chat like a library, okay? So I'll try to put in like chapters and all that. But I mean, I'll give you an example of what I've done with the other classes. So yeah, something like that, right? So it's just a whole list of like recordings and all that, and then they just refer to it. This is my IB class, okay? But yeah, so that's the it's empty now because I haven't gotten any requests yet, like since August 2nd. So please feel free to go ahead and ask me for the recording. You don't need to type in here. You just DM me and then I'll just fill it in so nobody will know that you're asking for it. Okay, right. Sorry, morning problem. Yeah, I mean, I can only do so much in one lesson a week, right? Especially if you're already not an A grade, right? And you're trying to climb, right, up to the A grade, right? Those are the resources I provide for you. Okay. Yeah. So I think in a way, no excuses, right? The water has been brought to the horse. Okay. This question though, wow. This vector diagram question. Anyone having troubles with this vector diagram question? I had trouble on this on Monday. What? You had trouble with this, right? Yeah. So the thing about this question was that, sometimes when I read questions, when I read this kind of questions, I get a sense of like what the teacher is trying to do, right? So, at a certain level, you also try to do that, lah. You try to see like, oh, the teacher is trying to be funny here. Okay. So one thing that the teacher did not did not really say in or declare in detail is the fact that this thing, right, this boat, right, this boat is gonna have a resultant force pointing towards the left, right? You realize that they don't say it explicitly anywhere. The only thing, okay, the only thing that you can see is this. It says one crewman pulls 130 newtons at an angle of 34 degrees, right? An angle of 34 degrees relative to the forward direction, right? So that was the only clue, which also means that the resultant force acting on this boat is pointing directly to the left, horizontally directly to the left. Because if you read the rest of the question, you realize that there are actually two unknowns. You don't know what this force is, and you also don't know what's the resultant force, right? So that's a problem. It's always a problem when you have two unknowns, right? Because then you have to find more information. Okay, so if you look at the vector diagram, right? They say by means of a skill diagram, determine the size of the resultant force by the two forces. So it's going to be a problem because I don't know what this force is. Okay, but we'll work this out together. But now that you kind of like heard me say it, that the resultant force is pointing towards the left side, right? Then we do our standard procedure. So for vector diagram, let's try again one more time, right, from the beginning. So those who have the two-side printed ones, right, the diagrams are going to be a little bit smaller for you, right? Those who have printed on one page itself, the diagram is going to be bigger for you, right? Do you have space, or do you try drawing and then there's no space, you didn't try drawing? Okay, all right. So give me a scale. Yeah, what scale do you want to use? So the only force that you have is what? The only force is 130 newtons, right? 130 newtons. So that's the only force you have, right? So looking at the size of your paper, like, 1 cm is to how many newtons is good size? 1 cm to how many newtons is good size? Kai and Joshua, later on I need an update from your regarding your school. I'll ask you in a while, but let me finish this question first. Say what? 1 cm to 10 newtons, right? That's nice for you because you have one full page, right? So because if it's 1 cm to 10 newtons, that's a 13 cm line. Can you fit a 13 cm line in your half page? Yeah, yeah, it is, but you're stretching it, right? Your resultant force is going to be bigger than 13 cm, so that's not a good scale for those who are having half pages. So those who have half pages, you got to decide the scale. Hey, you have to decide the scale first before you do anything. What's the scale for the half pages one? Wee wee. Yeah, I mean, if it's 1 cm to 10 newtons too big, then choose 1 cm to 20 newtons, right? So which means that the 130 newtons will be how many cm? What do you choose? Your diagram looks a little small. Did you choose one? Wait, you didn't write down the scale? You have to write down scale. First step, write down scale. First step. Don't draw yet. First step, write down scale. Write down the scale. 1 cm to 20 newtons, write it down. Alright, okay, fine. Alright, I'll lead by example. Goodness. 1 cm is to 20 newtons, right? For those who are using the half pages, for those who are using like full page A4 size, go ahead, 1 cm, right? 10 newtons, that's fine. Okay, right. Then what's the next thing that you need to do? Guys, what's the next thing you need to do? If you remember my steps, what's the next thing that we do? Draw scale, and then draw scale, and then do a quick sketch. Quick sketch. How do you think the diagram will look like? So the problem is, if you can't come up with this quick sketch, then you're really stuck, right? So you had to know that the resultant force of those two forces, right, according to the question, even though it's not explicitly stated, the resultant force is pointing where? Huh? To the left. I thought you said F. All right, to the left, right? To the left, right? But horizontally, like legit horizontally. So do a quick sketch down here like this. This would have been the resultant force, right? This would have been the resultant force. But how would the other two forces look like then? Right? So what happens is, in the other classes, the other two classes, right? I mean, there's a benefit being the last class of the week, because you kind of like, you can hear what the other, the common mistakes the other two classes make, right? Okay, so, right? So if you have like a resultant force here like this, right? Then you have this force here and this force here, like that. Okay, now if you draw it like this, you might be in trouble, right? You might be in trouble because it's like, one of these forces, you don't even know how big it is and all that. So it's going to be very hard to draw a parallelogram. Okay, so I will always try to recommend you to think of the tip to tail method, all right? But some students have like difficulty trying to do that. So you know what I'm going to do? I'm going to just show this diagram here for you. All right, so we have one force here, right? We have another force here like this, and the resultant force is pointing towards the middle, right? The resultant force is pointing towards the middle, right? I would suggest that you use the tip to tail method. So down here you can do the sketch. So all you have to do is learn how to shift, right? Shift the forces, right? So that it can give you the resultant force. So that's how we shift it. So we shift this one over here, right? And we shift the force F over here. So this is your 130 newtons, and this is your force F, right? I mean, that's the idea of it. Right, and this is your F net. Okay, right? Let me just show you some of the common examples that's the other students some of the common mistakes, right? One of the not common, I would say it's a major mistake. So there's always this This one, like, I was really angry with him that day. So there's always this problem, okay, where students, they try to make it simplistic, right? You can try to simplify it, but if you try to make it simplistic, then you're not going to get the whole idea. So what he did was this, okay? He had like one force there, then he drew like a 130 Newton force here like this, okay? So you know how some students, like, in their minds they're just thinking like, oh, vector diagram is a triangle, it's a triangle. I need to draw a triangle. Then he drew it like this. Yeah. So it's kind of like, it's one thing to teach you the right thing to do. It's another thing to have to ask you to correct your bad habits. Like, I had to, like, flush it out of his system, because in his mindset was that he's just very adamant on thinking about, like, but it's a triangle. I just need to draw a triangle, right? Yeah, it's not as just as simple as just drawing a triangle. Okay, I mean, so I had to ask him, can you think carefully about this? This man is pulling the boat this way, this man is pulling the boat that way, and you're telling me that the boat is going this way, the boat is gonna crash into the thing like this. So yeah. So obviously he felt like, oh yeah, that's wrong, which is great. But there were, like, I'm just sharing with you, like, in my years of experience, there are just some lost causes out there, right? Really, there are just some students that are just lost causes. They, like, there was once also I did something similar like this. Oh, this one pulling here, this one pulling there. Are you telling me that the resultant force is pointing this way, and therefore, the boat is going to crash into or, like, the thing is going to move downwards? The response was like, yeah, that's what the vector diagram shows, what. Okay, right? So, but there are lost causes out there, right? I mean, yeah, yeah. I guess he's just gonna lose the mark in the exam, right? So I'm hoping that you guys don't have that kind of. It's actually not even about aptitude. It's about the attitude to it, right? It's, yeah. I mean, I have zero qualms about, like, you not having aptitude, right? But I have, like, major concerns if your attitude is that sort of, like, nonchalant, like, yeah, that's what the vector diagram shows, right? Yeah, thing. The vector diagram is what you draw. You're trying to show someone where's the resultant force, right? It's not like, you kind of, like, you just draw it and then that's it. Okay, so on the sketch here, it'll be something like that. You will have the 130 here, right? 130 near, and then you will have the, right, force F here like this. Okay, so that's the sketch. And this is your bottleneck. Like, this is like the crucial point on the in the question, because if you can't get this sketch out, there is very hardly any way you can draw the full thing. So I will want you to draw a sketch first, right? So scale, then sketch. Okay, scale, then sketch. Scale, then sketch. Then you draw the whole thing. Okay, then you draw the full thing. Okay, so when you're starting to draw, what's my mantra for this? What's my operating procedure for this? What's step one? Scale, sketch, then step one. What's the first thing I always ask you to do when you draw vector diagrams? If you don't remember, it's okay, but by after a few more times, right, you're gonna like you're gonna feel that I sound like a broken record. Come on, what's the first step? Step one. Okay, draw what you know. Draw what you know. Okay, so the thing, but it really depends on how you want to draw it from like, depending on your experience level. Okay, so some people might want to draw the 130 first, right? Or some people might want to draw the resultant force first. Okay, well, actually you can draw both lah. So draw what you know. We're gonna start drawing the we're gonna we're gonna start drawing the resultant force first. Okay, so we're gonna draw this resultant force pointing over here. All right, so we're going to draw a resultant force pointing horizontally across. So that's the only thing that we know for now. So we're just going to draw it. And you realize that you don't even know what how long this line is. Doesn't matter, right? You just draw a double arrow on this thing here and understand that this will be a resultant force, because according to the question, this is supposed to be the resultant force. It's supposed to be a horizontal line. Good. All right. So what else do you draw now? What else do you draw? Come on, tell me what you want to draw now. You want to draw the 130, which is how many cm? 6.5 cm. All right, for those who have the print out half half. right? 6.5 cm, right? And you gotta have your protractor, man, right? If you ain't got protractor, then you're in tough luck, right? So what's it? You need a ruler as well. Goodness, you all need everything. Okay, protractor, ruler, protractor, set square. You want what? You want a ruler? I have one more. I have one more here. Oh, you got ruler. You got ruler. Okay. All right. All right. Let's do this. All right. Let's do this. So we measure out 34 degrees. Okay. Now here's the other thing, right? If you don't know how to use a protractor, I ran out of protractors. You know what? I'm gonna have to buy new protractors. Can someone after using it pass it to her? Pass her protractors. Oh man, yeah, I better go buy some protractors, man. I mean, I had some and then it's all disappeared. Go Taobao, go and buy those mega packs. Tava, just hang on for a while. Oh yeah, just pass it lah. Yeah, just pass it. Once you're done with it. Okay? Alright, coolios. Alright. So, and then you draw that. And then you draw you draw that 136.5 cm line, kind of like this. Right. I don't know, man. I'm just yeah. Right, you guys measure 34 degrees and then you measure your 6.5 cm for the 130 newtons. Put an arrow there. Put an arrow over there. Right, so there you go. Right. And then what do you do next though? What do you do next? This probably is the next tough part. Right? How do you draw F? So like I said, you draw what you know first. You know the resultant force is here. You know the 130 newtons is here. You're just one step away. You're just one step away. But how do you know what angle it is? 45 degrees? Then you're just gonna freehand it? Oh, you already measured it? Okay. So we do know that F is 45 degrees, right? It is 45 degrees to what? To the horizontal, correct? It's 45 degrees to the horizontal. So some of you might be like, okay, then you know guys, construction, right? Just be daring with it. Like kind of like if you know that you need a horizontal line here, then you just draw a horizontal dotted line, right? You just draw a horizontal dotted line. Nobody's gonna fault you for that, right? You draw a horizontal dotted line here, you measure 45 degrees from there, right? You measure 45 degrees from that one there. Okay, measure 45 degrees. Right, yeah, all my numbers are obviously fake. But yeah, there you go. Right. And then you connect the last bit, right, up to the point where it joins the thing here like this. Are you doing vectors in E-math already? Are you doing vectors in E-math already? Yeah? Yeah? You know A plus B equals to C vector, right? You know like in math it's actually more like in math the vector addition is even more like stringent than physics, right? Like you gotta do like A with an arrow on top plus B with an arrow on top equals to C with an arrow on top. Am I right? That's what you have to do for math, right? Like physics, we don't even do that, man. Like we're like, okay, just draw it, dude. We don't need the formality. Let's just get it done. But yeah, okay, that's it. That's all there is to it. So what's your job now? Your job is to measure this distance here, right? And then that's your resultant force. And how much would that be? 180, 180 newtons, right? 180 newtons. Okay. Did you realize that they didn't ask you for F? Did you realize they didn't ask you for F? Yeah, they didn't ask you for F, right? So, but if you had to find, could you find it? Yeah, you can, right? Okay. Let's try. Let me. Okay, so I didn't do this with the other two classes because I was tight for time, right? Today I think I have a little bit more stretch here. Okay, let me try to twist the question a bit. Okay, right? Not too much, just a little bit. Okay, what have you just drawn? I know your vector diagram to find what? What's the purpose of this? To find the resultant force of what? Of what? Resultant force of the boat, yeah, which is due to what? Okay, due to the forces, right? Due to the 130 newtons and the pulling force, right? Okay, resultant force, right? Okay, but here's the thing, okay? You shouldn't say the resultant force on the boat. That was wrong. Specifically, what was the instruction of the question? Look at the question. What was the instruction of the question? Resultant force of the two forces. You get what I mean? Right. Okay, look at the boat. It's a boat, right? So what's it sitting on? It's sitting on water, right? Would you expect water resistance? How come there's no water resistance inside this question? Why didn't we consider the water resistance? Why didn't you consider the water resistance? No, don't say that. Why didn't we consider the water resistance? Exactly, Kyrie. That's exactly what you're. That's exactly true. All right. The question is very specific. The question simply just wants you to calculate the resultant force of the two forces without considering anything else. You get what I'm saying? Like, so yeah. But what if I tell you this, okay? What if I give you an extra part, right? Maybe like a part C, for example. I add on this. The boat is moving with constant speed. Explain why. Let's say I give you a part C here like this, right? So, right, part C, boat is moving with constant speed, right? Explain why, right? This is like a 1 mark question, right? So you have to learn how you got to learn this thing, okay? So when there is a resultant force, guys, when there's a resultant force, right? What should there have been? Acceleration. The boat should have acceleration. The boat should have been accelerating, right? For part C, bonus question, right? The boat eventually moves with constant speed, or rather, the boat is moving at constant speed. Then I ask you explain why. So how do we explain this? No, whatever I just said lah. Due to the water resistance, right? Due to the water resistance, right? Okay, I'm gonna ask you this, okay? The water resistance is how much? Yeah, exactly. So the explanation for this, right? The boat is moving constantly. Explain why there's water resistance, right? Water resistance of 180 newtons acting to the right. Acting to the right. All right, like no, perfectly horizontal, acting to the right. F net on boat or of boat is 0. Okay. So very specifically, the question only asks you to draw the resultant force of the two forces. But if you're looking at the boat, you have to consider the water resistance. And therefore, pardon for the bad handwriting. I blame the program. The program is shitty, right? Right, they don't capture my handwriting well enough. So the water resistance 180 newtons is acting to the right. Okay, the F net on the boat is 0. That's why it's moving at constant speed. That's yeah. That's how it's done. We good? Yeah? Okay, good. So, no, unfortunately, I didn't get to do this with the other two classes because I was very flustered with my tech that day. Right, never mind, I'm getting my stuff fixed. I have to go and buy a new computer. I'm freaking annoying. It's like Windows 10 is no longer supported. I have to go and get Windows 11. What? Why do they do that to us? Okay, anyway. Alright, question 2, anybody? Do you need me to do question 2? Any explanation stuff that you... Was it what? The last part, yeah, the last part, yeah. State and explain what happens when string B is put down with a quick jerk. How about B part 1? How about B part 1? Let me go through B part 1 first, okay? Right. So when you pull this string slowly, okay, when you pull this string slowly, you're basically exerting like a lot of force on string A, right? Because string A has to do two things, right? String A, right? The tension in string A, right? TA, the tension in string A has to support both the TB pointing downwards as well as, right, the MG, right, of the anvil pointing downwards. Right, so down here like this. So tension in A is equals to mg plus the tension in B. So if both strings are identical, if you continue to exert more and more force on string B, right, more and more force on string B, right, string A will eventually snap first, right, because the amount of tension in string A will always be more than B, right, if you pull slowly. So you got to remember this, that I pull the string, right? When I pull string B, right, does it immediately affect string A? Does it immediately affect string A? No, right? So when I pull string B pulls the anvil, anvil pulls down on the string A, right? So it's kind of like part one, no, it's like a daisy chain, right? So you got this one, then this one, then that one, right? Okay. So for part two, I mean, I've already covered part one, why string A snaps first, because the tension in A is the sum of mg plus tension in B. But if it's in the second part where they ask you, what happens if I jerk, right, and pull string B, okay, with a quick action, right, then the idea is that B will snap but not A, right? And the reason is due to inertia of mass, right? So for the first part, what was it again? I pull string B pulls mass M pulls string A, right? Then string A will snap. But if I do a fast action, I pull string B very quickly, right? The amount of force that I apply on string B is likely to break string B first, right? Before the mass can pull string A. So it's due to inertia of the mass, right? The whole answer there, I think the 2 marks there, is it 2 marks? It's basically just you saying that, okay? So the answer is this, right? Due to inertia of mass M, when a large force is applied on string B will snap first before string A. That's it. That's the 2 marks. Due to the inertia of, write it down. Due to the inertia of, and don't use black pen, use blue. It's a thing. No, you don't have blue pen? Then, yeah. Use green, right? If you want also. Yeah, use green also can. Yeah, use blue also can. Basically, as long as there's a color different from black, right? Because I want you all to see your work carefully, like more apparently. Sorry, let me just settle one thing. Okay, so due to inertia of mass, and that's pretty much it. Okay, come next question. I'm not going to go through every single question. Let me know which ones you want me to go through. So the other students required this, but that's just because he didn't realize GP is just strictly based on height. Yeah. Anything else? Anything for question 3? Right. You got to check the answers though. Have you checked the answers yet? Yeah, you got to check the answers. Yeah. Yeah, I do things a bit differently. I don't mark your work, right? Cause I ain't got time for that. I'd rather spend the time going through these things. What? You want part C? It says determine the KE of the ball at position A. Where's position A? Oh, this one here? They want you to determine it. Okay. Is there friction on the slope? No friction. So what you got to do is you need to, all right. You need to figure out how much GP is there here. How much GP do you have in all there? MG13, right? Correct. Work backwards, dude. Work backwards. So if you work backwards, then how much GP did he have here? That'll be what? MG 7.5, right? Okay. Yes. Then this one minus this one, that's the KE that you have there. Yeah. I know it's a bit weird because it's like, oh, but I don't like, in some of you might be thinking, oh, KE, I need to half MV squared. Then you don't have V, then you're stuck. Then you're like, oh, I don't know how to do this really. Right? So you got to do energy accounting. This is called energy accounting, right? So you account for the amount. Like I always say, it's kind of like it's a zero sum game, right? You might hear jargon like that from time to time. Zero sum game means that however much energy you have here, it will be converted to whatever it has at the end, right? So if at the end you have mg13, then the total sum of energy here would have been mg13 as well, okay? But since the GPE here is mg 7.5, then I can, I can reason out that the amount of Ke here, right, would have been the difference between Mg13 and Mg7.5. So what did you get? 44 joules? That's the answer. Is that the answer? Oh, there's friction. Oh goodness, I didn't know there was friction. Nobody told me it was friction. So how much friction is there? 10.7 joules of thermal energy, right? So internal energy, right? Okay, 10.7. So you gotta add back. So this Mg13 is the Ke here plus the Gp here plus the friction lost. Yeah, sorry, the work done due to friction here. Right. So this is what, 10.7 joules, is it? 10.7 joules. So you have to do some accounting. So let's just do the accounting. Okay, it's like, okay, I give you an allowance, Mg13, right? What do you spend on? Right, I spend on heat. I spend on. I used to have Mg 7.5. Okay, and then after that I have the Ke. Right, there you go. Okay, total energy of the system is conserved, like that's what they're saying. All right, there you go. All right, can I move on to the next thing? Right, so you have to figure out what's the value of that. Number 4, anyone? Number 4? Number 4, always right, number 4. Okay. Number 4, what's this device called? Yeah, manometer. What's it meant to, what's it used to do? Say what?
Measure pressure.
Absolutely wrong. Yeah. So you see, right, there are some phrases I want you to memorize. So please try to memorize those. Otherwise, I'm just repeating the same old thing. Then you think I'm an old nag. Right? I'm not an old nag. You're just shit at memorizing stuff. Come on. What that compare pressure? Okay, so when you say measure pressure, that actually doesn't even fall in any category, right? Okay, you probably might be mistaken. Barometer. What does a barometer do? Barometer. Oh, come on. Manometer compare pressure. Barometer does what? Barometer. Yeah, measures atmospheric pressure. So you saying measure pressure itself is no meaning on. Okay? Alright, so yeah. So this is the manometer, it's comparing pressure. Which pressures are we comparing? You say compare, right? So which are the two? Atmospheric pressure and gas pressure, right? So like okay, intuitively, which one has a higher pressure? Gas or atmosphere? Atmosphere has a higher pressure. How do you know? How do you tell? Okay, fine. All right, so that means atmospheric pressure is able to push the liquid level down further than the gas pressure, right? Okay, good. What's my standard procedure for manometer? I got a standard procedure. What's the standard procedure? I mean, yeah, whatever's above is the pressure. That's good. But what's the phrase I use for pressure? I give you an example. Same. Nice. What's the phrase I always use for pressure questions? Same liquid, same level, same pressure. Okay? You heard me say that before, right? Same liquid, same level, same pressure. You heard me say that before, so stick to it. Same liquid, same level, same pressure. All right? Okay, what does that mean? What does that mean? So in the same body of liquid, which is this one here, you see this liquid here like this, right? At the same level of this liquid, they have the same pressure. What that means is that you have this here and this here, they have the same pressure. Right, they have the same pressure. Yeah, there you go. Okay, and then whatever's above is causes the pressure, right? So like what Isaac said, right? Look at this. So what's above point Q here? What's above this level here? Atmospheric pressure, right? So, right, that's atmospheric pressure. What's above this point here? What's above this point here? Hello, good morning, guys. What's above here? The liquid and the gas. So on Tuesday, I had one who had this misconception thinking that the pressure is due to everything from all directions, which is not right. You know my style. Pressure is due to whatever is above, right? Above. So whatever is above this level here is the liquid and the gas pressure. So the gas pressure is acting downwards like this, right? Acting downwards like this, and the liquid pressure is acting downwards like that, right? On that one there. So you know what? Let's write the equation. So atmospheric pressure, ATM, PATM, equals to, right, H rho G, which is this H here, the small height of liquid there, plus the pressure of the gas, right? Isn't that right? We're not done yet. So what do they want? They want us to calculate the what? Pressure of the gas, is it? They want us to calculate the pressure of the gas, right? No, I mean if you rearrange it, so the pressure of the gas will be equals to, right, PATM minus H rho G, right? PATM minus H rho G, right? Did they give you atmospheric pressure? What units did they give you in? Pascals, right? Is that the SI unit of pressure? It is, right? So if this PATM is in pascals, you got to make sure that H rho G is in pascal as well, right? So I mean it will be. So if you take the H times the rho times the G, you get pascals. So PATM is what? 1 times 10 to the power 5. 1 times 10 to the power 5. Minus away H rho G, right? H, which is 1.9, right? Because that's in cm, you got to change it to meters. Rho is in thousand, so it's already in SI units. Okay, right? And then times G, which is 10, right? We take G to be 10. I think for Kyrie, you have to use 9.8, right? Sorry about that. Everyone else is 10, right? I don't remember. Everyone else is 10. Okay. Yeah, so yeah, work this out and you should be able to get your answer in pascals, which is exactly what they want. Okay? Yeah? Right. Now, I will tell you this, okay? What if I show you, like, I'm gonna do a bit of side quest again, right? You know me, right? When I do papers, I don't just do like the question itself. I like to do a little bit of a side quest, give you a little bit of more in-depth understanding, right? Not for fun though. This is not enrichment, right? So it's like the thing that you need to know. I'm gonna ask you this though, like, can I present the pressure of this liquid in another way? Can I write another units for the liquid pressure? Like, this liquid here, I just circled it, right? Can I present it in another way? How would I present it in another way? Anyone? No? Okay, I can write it like this. 1.9 m H2O. I can write it like that. Anyone visibly confused? No? Huh? Yeah, it is. It is. It is basically like MMHG. Do you know what Hg stands for in MMHG? Mercury. That's a chemical symbol for mercury. So don't think that the Hg is this Hg here, right? That's a very common mistake. So 1.9 H2, 1.9 meter H2O. You could also write it as 190 cm H2O as well. You could write it like that. Yeah, you could write it like that. You get what I'm saying? Okay, but just make sure, is this SI units? Are these two SI units for pressure? No, they're not. SI units for pressure is pascals, right? So you gotta have to leave your answer in pascals, right? If they want you to write it in pascals. So you might have to recurse for the pressure thing. Did you attend the pressure revision in June? Were you here in June? No, you were not. Okay, so you might have to, like, you obviously, like, I can see like you obviously need a bit more help for pressure. Okay, so ask me for the pressure video. I think once you're done with that lesson, I think you should be able to catch it very quickly. But more importantly, what's the final value here? Sorry. Oh, what? 8.1 times 10 to the power 4? Yeah? Okay, 8.1 times 10 to the power 4. 81,000? 81,000. 81,000 pascals. I'm just going to write it like that. Right? 81,000 pascals. Okay, good. So that's for the liquid pressure, right? That's for liquid pressure. So what happens in the next part here is that they say that they use mercury. Like guys, if you haven't marked it right and your phone is next to you, you can just open up the answer key right like here. Like you can go to the shared folder and just open it up and then check your answer as we go along. Yeah, it's there, right? Because you were asking me whether you should mark your paper, right? Yeah. I mean, if those who haven't marked it, you should just open up the answer key and just keep it to the side. I'm not going through every question. I'm not marking a paper either, right? I think I will only request you to send me pictures of your written answers when I want you to send, right? But for now, we're just learning all the, like, learning all the basic stuff. Okay, so in the next part, instead of water, they want you to use mercury. Instead of water, they want you to use mercury. Okay. So the question is, if you replace it with mercury, what would be the difference between the height levels? Right. So what they want you to do here is literally convert 1.9 meter of H2O, and they want you to convert it into right meters of Hg, like that. They want you to convert from 1.9 meter H2O to how many meters of Hg. Right? There's a few ways to do this, but once you're very familiar with this, right, you can have a shortcut, but I only allow you to use shortcuts when you're familiar with it. If you're not familiar, please don't go and use the shortcut, right? Yes, as uncomfortable as it sounds, I rather you learn the whole thing, right, from scratch. Right, we have H rho G, right, equals to H rho G. The purpose of this is to show you how to convert between two liquid levels, right? We have H rho G as 1.9, we have water as 1000, right? Density is 1000. G cancels out, so I don't have to care about that. Then we have the H of the mercury, which is unknown, right? And then multiplied by the density of mercury, which is given here 13,600. 13,600. And therefore, what is the H then? Here, what is the H? What'd you get? 0.139, right? Good, yeah, 0.139, right? 0.139 meters, okay? Yeah, I mean, it is what it is. So what that means is that you have 0.139 meters. What's that in cm? You can write it as 13.9 cm mercury. You can write it as 139 mm mercury. Right? You can write it in all these things, right? But you got to remember the Hg at the back here is mercury. So that's the like the very common confusing thing, right? Among some students, they think that this Hg has something to do with that rho Hg there. No, that's not. That's the mercury thing, right? That's a symbol for mercury. Funnily enough, I think some teachers actually they purposely don't say it, they intentionally don't say it out. They don't tell you that this Hg is mercury, right? They just kind of like, haha, like you made a mistake, this sort of thing. So I'm telling you that it is like, it is different. It's not the same thing. Okay. Yeah, I mean that's the answer, lah. Right? 0.139 meters, right? 0.139 meters, right? That's the mercury level. Let's do this, right? Let's do this. Since you mentioned about the barometer just now. Okay, what's the purpose of a barometer, guys? Was that measure atmospheric pressure, right? Okay, good. So typically a barometer, what liquid do we use inside? Yeah, we use mercury, right? Hang on, let me just. Oh gosh, my computer is working overtime now. So we have a barometer kind of like this. All right. Okay. So if it's a proper barometer, what's at the top? It's vacuum. Right. So this is the ideal barometer. It's a vacuum on top. Right. So it shouldn't affect your readings. To find the atmospheric pressure, because barometer is used to do what? Measure atmospheric pressure, right? Okay. Let's say this is mercury. What's the density of mercury again? You see, even look at this symbol, guys. Look at this symbol. What did I write? I wrote rho Hg. You know how confusing that looks? You understand how confusing it can be now, right? But this is not the equation now. No, this is what was this? This is the density of mercury, right? Which was how much? 13,600, right? Okay, so I'm just gonna leave it there. 13,000 kg per meter cube. Okay. What's a typical height for atmospheric pressure? What's the usual height? What's the usual number that we have for mercury? 76, yeah, 76. But it fluctuates, right? So it's not a number for you to memorize. Don't go memorize it at like 74, 75, 76, 77, right? So it's around there, 76, okay? But measured from where to where? Where's the 76? Measured from where to where? From which level to which level? From the bottom here at the basin to the top. So surface to this level. So mercury level to mercury level, right? Okay. So you have to remember this because this is the thing that some students they make mistakes on, right? So you have to measure this distance. Like this is the H that you have. You know what? Let's not assume that it's 76. What was the pressure given in the question just now? How much was the atmospheric pressure given just now in the question? Was that 1.0 times 10 to the power 5 pascals, right? So that's 100,000 pascals. Okay, 100,000 pascals. Good, good, good. All right. I want you to convert it backwards. I want you to do it backwards now. I want you to find out what's the height then for this barometer. Yeah, what should the height be? Say what? 0.73 meters. Is that right? Okay. So based on 100,000 pascals, this height here, you look at it, it's not even 76, it's 0.73. So we have 0.73 meters, right? Or you can say 73 cm or 730 mm, right? And I also want to present to you the way that how sometimes the question can show you, right? What if I show you this? Okay, 1 atm. What's 1 atm? 1 atmosphere, right? Which is the same as this lah. P atm and 1 atm mean the same thing, right? They're just trying to like be funny with you, right? 1 atmosphere like this, okay? Which is equivalent to 100,000 pascals, right? 100,000 pascals. You can write it like that, 100,000 pascals, which is also equals to, you can write it in a way, right? 73 cm Hg, right? I can write it like that as well, 73 cm Hg. Can I get another decimal? It's not exactly 73, right? Was that 73.5? Yeah, okay, all right. I will prefer to have a little bit more, because if you're using a ruler, you should be able to measure up to like 1 mm, right? So you should write it as 735, right, meters, and therefore you can write 73.5 cm mercury, okay? Yeah, I'm not comfortable with just using like whole number, you know? Yeah, we have to kind of like respect the instrument, right? Okay, so we use the instrument's precision. Any issues on this so far? No? Okay, you know what? Mercury is toxic, right? So what happens if I try to use water? Yeah, but how tall? Don't tell me too tall. Figure it out. Tell me What happens if I convert this to water instead? Like, you know, like I want to use water instead. Like if it's water, yeah. If H2O, what will be the height then? Right? The height will be 13.6 times taller than this 73.5. Because the density ratio is 13.6 times. So the height of water would have been, yeah, how much is that though? Work it out. Come, give me the value. Give me nice, like the unrounded value first. So H times 13.6 times 7.35 cm. That's the amount of H. I mean, yeah. How much is that? Huh? How do you key in wrongly? It's just two numbers, dude. What? 13.6 times 73.5. What'd you get? What's that? 999.6 cm. Is that right? Yeah, okay, that's fine. I mean, rounded off is what? 1,000 cm? Right? So that's just 10 meters. You're right. Okay. So yeah, there we go. 10 meters, 10.0 meters. That's fine. Do you know what that means though? Like, how tall must your boiling tube be? How tall must this tube be? Was that what? No, dude. Like each floor is what? 2.5 stories? No, 2.5 meters. Each story is about 2.5 meters. You need about 4 stories high. No, and not only that, You cannot just have a tube that is 10 meters. You gotta have some. You gotta give them some space, right, to show that there's a vacuum up there, right? So you probably need like an 11-meter tall boiling tube. That makes no sense, right? I mean, if you go on the YouTube and go and search for guys like Steve Mould, right? He did this. He used a rubber tubing instead. He used because it doesn't matter what tube you use, right? He used a rubber tubing. So he went up a stairwell. Your stairwell, you got the railings, right? Then there's a central area where it's like empty, right? So he strung up the entire tube, right? And then basically see how much water he can use his mouth to suck up. Like, I mean, it's just rubber tubing, right? He did I think he just used some clean rubber tubing, and he just, sucking up the air, like, trying to get the water to come up, right? And like the most you can reach is about like 10 meters. Okay, we good? All right, not done yet though. You know what this means? It means that every atmosphere, every 1 atmosphere, right? 1 atmosphere is equivalent to 10 meters of water height. 10-meter H2O, right? 1 atmosphere is equivalent to 10 meters of H2O. Yeah? So let's say you go diving and you dive to 20 meters. Right? So let's say you go diving and you dive to like 20 meters below water surface. Right? 20 meters at 20 meters of water. Right? 20 meters of water. Let's say you dive up to this point here. What's the pressure here then? Around 3 atmospheres. Don't forget about the atmospheric pressure on top, dudes. Don't get tricked so easily. Come on. Right? Like I say again, simplify, but don't be simplistic. All right, excellent. So now you get the idea, right? Okay, don't get tricked. It's like I can't be there to just keep reminding you. Don't get tricked. Don't get tricked. Don't get tricked. I can't be there. You have to be extra vigilant, right? This is kind of annoying, right? If you think about this. Hmm. Moving on. Let's move on, yeah? Yeah, let's move on. Probably take a quick break in just a while. Let me know what's the next questions you want me to go through. Did I manage to finish everything? No, I didn't manage to finish everything. I did until question 8. Okay, next one, come. Tell me which ones you want me to go through. How about this one? Refraction of water waves. Refraction of wave fronts. Do you need this? No? Which one? The lenses one? Yeah, I'm going to do the lenses one. No worries. But how about this one? Tava? Have I shown you this before? No? Send me a request for this. So you keep track of what you need to send me, yeah? Don't wait until next week, you know? Like after class, right? Or if you want right now, you take up your phone, you just send me a request saying, can you send me the video for pressure and for this one here, right? So this one here is called refraction of water waves. This one here, I like to call it I mean, I have a phrase for this. It's called the slower, shorter, shallow water. Remember that nonsense phrase, right? So slower, shorter, shallow water. Okay, but frequency stays the same, right? I was trying to use like alliteration to help you remember. Slower, shorter, shallow water stays the same. Yeah, try lah. Okay, but anyway, so you know, just drop me a message and ask me for the recording of this, because if majority of them don't need this, then I'll just move on, right? Because yeah. So it says describe the change in depth and ask you explain why the change, right? So that video would have covered everything. Okay, so now I'm gonna go into this one here. This one's the painful one, right? I am going to screenshot a part of this and just put it onto my PowerPoint because it's a lot easier to draw with the PowerPoint. Okay, there we go. This one here. So what's the deal with this? What's the deal with this this diagram here? Sorry, so Isaac doesn't need this, right? You don't do lenses, so you don't have to worry. Do you? You do, right? Oh, you don't do also? Okay. You do, yeah, the two of you do. Okay. So for those who don't need this, I'm just gonna like go through this very quickly for those who need. Right. What did I say about lens diagrams? Like what's the deal with lens diagrams? What's your job? You have to memorize all 6 diagrams. You need to memorize all 6 diagrams. Okay? Right? You need to memorize it up to the point whereby I say that, oh, I have an image. It's real, inverted, and smaller. Then you have to memorize where's the object position, right? Where's this image, you know, and all that. So you have to memorize all 6 diagrams. But I have a way of memorizing it, right? I have like a very standard procedure of how to memorize it. Okay, so you know what to do. Sorry, there's something blocking the screen. Oh dear, hang on. Oh, okay. Sorry about that. Is that not okay now? Okay, sorry about that. Okay. So for those who need lenses, right? You know what to do, right? I don't know about you, Joshua, but if let's say you realize that there's one of those things that I was doing just now and you are not sure of it, you gotta send me a request for the videos. Okay, you gotta send me the request for the videos, right? If you feel that you're afraid that you'll forget later, just drop me the message now. Right, just say, oh, I need the video. Right, so you're supposed to memorize all 6 diagrams, okay, up to the point where it's like that, right? So what's happening here? Where's the object? The object is here. What's this dotted line here, Tava? What's this thing here? That's the what's this? That's the image. This is the image. Okay? What's up with the deal with the image? So you realize, right, that we're very, very used to getting the object and then they give us a lens, then we draw and then we find the image, right? This time around it's reverse engineering, right? That's why it's harder, right? Reverse engineering is always a little bit harder, right? Okay, so we ask ourselves, this image here, like, you know, what are the properties of this image? I mean, look at it. Tell me what's the properties of it. It's virtual. What else? It's magnified. What else? One key detail about this image. It's upright. Okay? It's upright. So there's only one lens diagram. There's only one lens diagram in all the 6, right? That has an upright and virtual image, which is a magnifying glass. Okay, magnifying glass. But that's not going to help you to draw this, right? So the way to do this question, like I think I can see that in your working, right? That's great. Okay, the way to do this question is always remember this. You know the 3 construction light rays, the 3 light rays to draw for lens diagrams. Don't know, right? No, don't know. 3 light rays. The one that passes through the middle, the one that horizontal, and then cut F. Yeah, those 3 light rays, right? Okay, you only need 2 out of 3, right? Okay, so those 3 light rays, like whatever lens diagram drawing that you get, you always draw the one that passes through the middle, because that's where it connects the heads of the object and image, right? Yeah, object and image, right? Okay, so what you do is this: you just take one line, right, and then you draw across the head and the image. All right, hang on, let me just draw it again, nicer. There we go. Once you draw that, the lens is right here. Right, you got that? Yeah, it looks like you got that also. Alright, so that's great. Let me just draw the lens first. Right, this is where the lens is. Okay, then how? What's the next thing? So they want you to find the focal length, right? They want you to find focal length. So this is going to be tough because they don't give you the focal length. But you know what? Let's just go with the same procedure. So after you draw this line that passes through the middle, what's the next ray you draw? The next light ray that you draw is the horizontal one, right? You draw the horizontal one. So let's draw a horizontal light ray. Yeah, start drawing. You draw a horizontal light ray, right? Okay. Like, where's it gonna go next? I think that's where you're stuck at, right? You don't know where's it gonna go next, right? I mean, essentially, where is it supposed to go? Essentially, it's supposed to go and cut at F somewhere, right? But we don't know where F is. But here's the thing, because it's a magnifying glass image, right? Wherever the light ray goes and cuts the principal axis, you trace it back, it should hit, right? If you trace back that light ray, wherever it hits, I have no idea where it hits, but it should hit the top of the image. What that means is that you just draw another light ray, okay, that is going through the image here, as well as that point where it cuts the, yeah. Let me just draw this, Yeah, there you go. Something like that. You see that? Yeah. And here will be your focal point. So there's always a little bit margin of error. Right, there's always a little bit margin of error, but I think you should be able to get your focal point now. So this will be your focal point. Oh, it doesn't look very nice here because it's, you know what, I'm just gonna put this here, like that, focal point. You okay with this? Okay, but you know what? I want you all to clean up the diagram. We're not done yet. I want you to clean up the diagram. So how do we clean it up? First things first, I want to make sure that, right, that you understand that these are all dotted lines. These are all dotted lines, like that, right? Why do I want to ensure that these are dotted lines, guys? Like, what's the point of like you know, if you use pencil to draw, right? You just take your eraser and just erase parts of it like this, so it looks like that now, right? Why do I want to draw dotted lines? What do they represent? They represent virtual light rays, right? They represent virtual light rays. These solid lines represent what? The solid lines represent real light rays, right? The solid lines represent real light rays. And then that's why you need to draw arrows on them as well, light arrows. Don't forget about your light arrows. Right, those are your light arrows. Not drawing? Yeah, there you go. So, yeah, kind of like a waste if you didn't get this by 3 marks. Scary though. So, this next one though, what happens if you replace it with a thicker lens? Yeesh. So this thing here is not very common knowledge, so I'll just go through this with you very quickly. If you have a thin lens, the focal point will be quite long. If you have a much thicker lens, your focal point will actually be closer. For those who take bio, you should understand this. Myopia. Bio? Yeah, myopia. Oh, okay. Eyeball lens? You don't even touch the eyeball at all? No anatomy of the eyeball? Okay. Anyone else who do bio? Yeah? Eyeball lens? Right? So the idea of myopia is that the eyeball lens is too thick. So the focal point is here. So when you have very distant object, the light ray comes in, right? It focuses at this point, but the retina is at the back. So that's why it's called short-sightedness. That's why it's called like you can't see far away objects, right? Because far away objects comes in as parallel lines, right? Parallel lines will always converge at f, right? So your retina is at the back. So thin lens can, okay. Well, so the idea here is this. So if you replace it with a thicker lens, what will happen? If you replace it with a thicker lens, your focal point is shorter. So let's imagine, let me draw a simulated one. Let's imagine that this is the new focal point. I'm going to call this f2, right? Look at f2, right? So what happens if I draw the light rays for f2? What happens if I draw the light rays for f2? So I draw the light ray. It's the same light rays, right? Like similar, right? The one that passes through the center is still passing through the center. I didn't change the position of the lens or the diagram or the object. But then now I have a shorter focal length. So this one here will bend like that. Oh, whoops. It becomes a real image. That's why I didn't quite like the question. Okay, let's just give it a slightly shorter focal length. F2 here, that is slightly shorter. Slightly shorter. So if it's slightly shorter, what will happen? Right, then you trace it backwards. So if you trace it backwards, what do you understand about this diagram here? What do you get? Huh? Larger image, right? Basically, it becomes more magnified. So the one thing about this question is that it's not a very fair question. It says converging lens replaced by thicker lens, right? Like you didn't tell me like how thick, right? So maybe they should have said something like slightly thicker, right? Not just thicker. Because if it's very thick, you have the problem that I did just now. I put the focal length here, right? I put the focal point here, and then when I started drawing, it became a real image on this side. So that's not what they want, right? So they didn't the person who said this question didn't realize that you're supposed to say like slightly thicker, just slightly. So do yourself a favor, slightly thicker. Right? So slightly thicker lens. Okay, how about the upper half of the lens is covered? What happens if I cover the upper half of the lens? Right? If you remember my original lessons, the image is still there. The image is still formed, but it's dimmer. It's sharp, but it's dimmer, less light rays formed. Less light rays form the image. Okay, that's all for this one. Okay, good. Then number 7, come. Let's come back to number 7. Right, what is your, do you need me to do 7? No? Hang on, I want to hear your answers though. How about these 2 marks here? Can you tell me what's your answer for this one? What do you say? No, it's okay. Don't need to read the answer key. Just tell me what you said. Uh-huh. Okay. Yes. Yes. No marks given. You lose the marks. You know why? Because you said that the protons are attracted. So that you can got to remember for static electricity, positive charges cannot move. So the only thing you can talk about is the movement of negative charges. Okay, so you have to say the negative charges are repelled to the bottom, right? And the top side is induced with a positive charge, right? Yeah, it's induced with a positive charge. So you cannot, absolutely cannot say that positive charges are attracted to the top. Okay, so if anybody writes that, right, I'll tell you this, okay? Even though the first part is correct, okay, even though you say the negative charges are repelled to the bottom, but the second part you wrote positive charges are attracted to the top. Most teachers won't give chance one. They'll just take away the marks. Yeah, most teachers they'll just put a cross and then that's it. Then you try to argue for the marks later on. You try to like fight for marks. They say no, cannot. Like it's obviously like to them, right? It's like saying that you're obviously not understanding the concept in full. So I don't think you should be awarded any marks. Okay, so that's the thing, right? Negative charges are repelled to the bottom, right? The top is induced with a positive charge. You can say that it's induced with a positive charge, right? But how about this one? State and explain the initial motion of the foil. 3 marks. Oof, 3 marks. Where are the 3 marks coming from? Attracted and moves up. 0. Okay. The key phrase in this question, right, is that it gets accelerated upwards. It experiences an acceleration upwards. So you're not wrong to say it moves upwards, but you have to say accelerate. Why? Because it's at rest at first. Since it starts moving upwards, it's accelerating, right? It has to accelerate. Okay? But then at the same time, you have to also emphasize why is it accelerating. So if you're trying to explain why something accelerates, right, what are you supposed to describe? You have to describe the forces. Okay? So I'll show you the full 3 marks, okay? I don't care what the answer key says, right? If you give me 3 marks to answer this, I give you my way, right? Because I'm pretty sure the answer key is a little bit shorty as well. Number 1, the force of attraction is stronger than the force of repulsion plus the weight of the foil. Okay? Force of attraction is stronger, right, than the force of repulsion and the weight of the foil, such that it will have a, so force of attraction minus the weight, force of repulsion minus weight, I'll get a resultant force, which causes it to what? Accelerate upwards. Okay, so if you realize that, you know, I'm playing this weird game whereby every time I say resultant force, you have to give me acceleration. That's the reason why. Okay, so FA minus mg minus FR equals Fm equals ma. We good? Right. So anyway, your answer here, the written answer here will be the force of attraction is stronger than the sum of weight and force of repulsion. Hence, there's a net force pointing upwards. Hence, the foil will accelerate upwards. Right. Those are the key phrases. Right. Don't try to replace any words. Right. I have to see the word accelerate. Okay. Anybody wants to check in? Why is the force of attraction stronger than repulsion? Yeah, that's right. Okay. So without you having to explain that, nobody's going to ask you to explain that. Okay. But I want you to realize that the force of attraction is stronger than the force of repulsion. Do you understand why? Why? Yeah, because the positive side is closer to the negatively charged object. Okay. It's just based on proximity. Okay, good. Like it's that close, right? It's that close such that it's even bigger than the repulsion and the weight combined, right? Which is why it gets lifted up. Okay, I did do question 8 with the rest of them, so I'm going to go through question 8 before I go back to nuclear, right? I didn't do 9, right? So 9 I can leave it for later because 9 anyway is nuclear, right? Yeah. Usain Bolt. Okay, never mind. We'll do the section B later on. This coming week, yeah. I did I already assign the next paper to do? Did I already indicate which paper to do next? I didn't? Oh damn, I didn't? I thought I did. Dang it. Wait, let me just ask the Monday people. Hang on, let me just make sure. Okay, so let's finish this up. Right. There is a error with this diagram though. There's a slight error with this diagram. Okay. The diagram looks a bit weird. Anyone wants to just point out where do you think it looks a bit weird at this diagram? It, well, um, well, maybe, yeah. I mean, one thing is that you don't see the wire, right? You don't see this wire, like kind of like it should be touching the second slip ring, right? Yeah, I mean that's one thing. But is there any other errors that you see here? It looks a bit weird, right? The slip ring is supposed to rotate freely, right? And the carbon brush itself is supposed to brush the sides of it, right? The original picture looks like this. What does it look like? It looks like the slip ring and the carbon brush like fuse to each other, right? How is it supposed to rotate, right? So do yourself a favor, right? Just draw a small little line here like this, just to show you that it's not the same piece of thing. It looks like it's like 3D printed to it, right? Right. So as this thing turns, right? It's just brushing against the carbon brush. We okay? Yeah, there we go. So this will be for um, an AC generator, all right? Then they ask you explain why the value of induced EMF is maximum in this position. What's your answer for this? Okay, that's fine. I also want you to kind of like can you add in? Okay, you don't have okay, saying that the coil is parallel to the magnetic field doesn't actually, it's not wrong, but it doesn't actually help you like like help the examiner understand why is it maximum. So I want you to write this instead, okay? Right. The sides of the coil, right? AB, right? AB and CD, right? AB and CD are cutting the field at 90 degrees, right? Cutting the field at 90 degrees, right? Hence the rate of change, hence rate of change of magnetic flux is maximum, right? So the induced EMF is maximum, okay? So it's cutting the field perpendicularly, right? Therefore, you get maximum rate of change of magnetic flux. Sorry, the handwriting is there is horrible, right? Rate of change of magnetic flux. Okay. What's the purpose of the component? It's a very silly answer, right? What's the purpose of the component? Yeah, to prevent the wires from getting twisted. Explain why in real power station, why is AC produced rather than DC? Step up the transformers to reduce. Don't say prevent. Prevent means you don't want to have. Reduce. Yeah, reduce power loss. Okay. Then okay lah. Do I need to go through the rest? No need. You double check the answer already. Opposite direction and 2 times the speed, right? Let me see your diagram. So it's twice the height and 2 times the period. Twice the height, everyone. Your graph 2 times the height. Alyssa, do it now. Hey, do it now. Let me see your one. Why? You forgot the twice the height. Do you know why is it twice the height? Why must the maximum induced EMF be 2 times? Is that because when you rotate 2 times the speed, you got 2 times the rate of change of magnetic flux, so the induced EMF is 2 times higher. 2 times as high, sorry, 2 times as high. Okay, at this point, take a quick break. I still got about like 25 more minutes, which like I have a lot more time, right, today, because I started on time and I don't have any technical problems like I did on Monday and Tuesday. It was so bad though. Let's look at the Nanhua paper 2. Hey, sorry. Let's not look at the what people do. Let's look at the nuclear question. Right. So we're gonna go back to the nuclear notes, but for now, take a quick break. Go back. Go and take your toilet break or snack break or anything, and then I think I'm going to use the restroom. Right. Those online, just give me a while. Oh yeah, no. Actually, I need to get your updates. Kyrie, can you tell me what you're doing in school now? It's like last time. When was last time, man? Last. Okay. What's the last topic you were on? I always forget one. Oh, AC generator. Okay, can. So the next one will be nuclear physics already. Okay, then for Joshua, finish syllabus, right? And what are they doing in school now though? Practical. Okay, okay, practical. Okay, that's good actually. That's good. Do you have a prelim practical exam coming up soon? 29th, the ACSI, I mean my ACSI guys, the express side, they just had their prelim practical, which was ridiculously early. And then I've got some people asking whether I can do another prelim practical. So I can do another practical consult this coming Thursday. I mean, I don't mind. I don't mind. But I just want to make sure that there's an audience though, because like the last time I asked for it, nobody turned up, right? So Thursday, are you able to? There's Thursday, same timing, 3:30, 3:15. Joshua, how about you? I don't know whether your schedule can or not. What do you mean by you don't know your schedule? The term three. Oh yeah. Please make sure, right? I'm gonna put down the calendar. As long as someone says okay, I'm gonna put down the calendar, right? And I believe I think the next thing I wanted everyone to do on Thursday, I'm just gonna put this down. Put down 3:30. This is the year 4 prac consult. Okay, prac consult. I actually want you all to pull out all your past practicals. Yeah, I want you all to pull out your past practicals, like collate your school practicals. Um, I don't know whether you can come in, but if you can come in, you can show me your practicals, or the next time you come in, next Sunday, right? You bring along your practicals, right? Yeah. Because the other one, I think Sasha already asked me for this practical consult because she said that she already prepared all her past practicals already. So if you can, everyone here, try to prepare your past practicals because I want to take a look at it, right? I want to help you get your your 15%, man. 15, right? Or is it 20%? 20, yeah. 20%? Oh wow, okay. The stakes are higher now. Is it 20% now? Or has it always been 20%? Damn it. I'm so bad at this. My memory is like shit. Uh, how many is a practical thing? What's this? Yeah, hey, sorry, Abigail, can you do me a favor? Can you just pass the snacks around, Alyssa as well? Whoever wants those things, just pass it around, right? And where it stops at, just leave it on the table there. 20%. Damn. And the practical is like 1 hour 50 minutes. Look at that. Yeah, 1 hour 50 minutes. It's like the longest paper ever, even longer than the structured papers itself. Yeah. Okay. Right. So yeah, we got a lot of work cut out for us, right? Those who have practical. So yeah, let's see. Yeah, practical assessments. Oh, interestingly, so we have all this. Look at that. There's actually a list of practical stuff. Did this happen before? Was it like that before? Let me check. The last time I saw a detailed practical was. Oh yeah, it was. Okay, that's fine. Right, maybe one of the practical consults I'll do that. I'll run through the syllabus. Like I'll run through the possible things that they can come up with. Yeah, this one here. Investigation of effects of EMI, magnetic effect of current. So all these, yeah. Oh wow. You know what? Yeah. And we don't usually see this in the prelim practicals I've been giving you. So I have to figure out a way of yeah. I'll tell you this, okay? Like I've yet to see this too. Like over these years. Wait, do y'all have the O level prelim practical book, the TYS book? What do you just nod your head? You're not tested on practical, right? You have a practical exam. How many percent is that? Oh wow, damn! You better be joining in the. I didn't know you have practicals. Am I supposed to know? Haven't started on teaching practical yet, but I've been holding all these practical consults. So what's the proper response to this? No, that's not the proper response. I already held the things before already. So what's the proper response to it? Yeah. Okay. So that's the proper response. Like, that's me and you, right? You ask for recordings, right? What you do with the recordings, I don't know. If you want to watch, you don't want to watch, also up to you, right? But that's what it is. Okay. Yeah. Do y'all realize that y'all have the O level TYS, or was it for A levels? There is a TYS for practical, you know? No, man. Joshua, do you know if there's a TYS for practicals? It's a TYS practical, right? There's a TYS practical book, right? Yeah, there is, you know. Yeah. It's new. It's like it came out was it last year or was it this year? I can't remember. I think it came out. It's new. Right. I tell you what. Next week I'll go and buy it. Right. Then I'll go and. Okay. Then you all have it also. Okay. Can. Right. So that's an add-on for those who are having practical exams. Yours is what? Do you have coursework? There must be some hands-on stuff component to your scores though. Please let me know. I'm supposed to guide you along with it. I already finished up with the ACSI guys. I finished up the IP ones. I finished up their projects already. You know, nothing, just pure paper. Okay, can. Dangerous, huh? Go and ask Amanda. Right? You like, you gotta have some skill set. Okay, anyway, yeah. Sorry, I said I want to go toilet. I'll go toilet, I'll come back. All right, let's continue this. About 15 more minutes left. Yeah. When was the last time I stopped for nuclear? Stability? Good, thanks. Okay. So if you remember, what did I mention about the stability? What's this? Like, what does the white region here show you? The white line in the middle. What's all that? Those are isotopes that are stable. Good, right? So the ones in the middle here are stable, right? What's the trend? The trend is when you're a when you're a small element, right? What helps you to be stable? Right? Notice how the white region and the red line kind of like coincides. Right? When you're a small element, um what's the trend to be stable? The proton number and the neutron number are equal to each other, right? So 1 to 1, right? Like, give you examples of what were some of the examples of small elements that are stable. What's that? Carbon what? What number? Give me the number. Carbon 12, right? 6 carbon 12. Anything else? Oxygen, right? 18, sorry, 16 and 8. Hang on, sorry. 16 and 8. Okay, anything else? Nitrogen, 14, 7. Yeah, right? Then I ask you, like, if they are stable, what do they not do? If they're stable means what? Yeah, they won't decay, right? Okay, so then what will make some isotopes decay? What's wrong with them? Like, generally three main things, right? What's that? Too heavy. So the too heavy ones are where? The too heavy ones are here. These guys are too heavy, so they will decay, right, in a certain way, correct? Okay. What other things? So what? So too many protons or too many neutrons, right? So you notice here in the gray region here, these are isotopes that have too many protons. In the yellow region here, these are isotopes that have too few neutrons. Too few neutrons being, like, meaning that there's too many protons, right? So you get the idea that basically nuclear, right? Nuclei, they decay because of this imbalance. But it's not a matter of like, oh, more neutrons is better or less neutrons is better. It's like you could have too many neutrons or you could have too few neutrons as well. Okay? Right? Or you basically have too many of both, like too many protons, too many neutrons, right? Okay, good. So yeah, that's what causes the nuclei to be unstable and therefore it will decay. So let's jump straight into it. Let's jump straight into the decay. So when these unstable nuclei decay, when the unstable nuclei decay, unstable, right? When they decay, okay, right? What's the point of doing that? What's the point of decaying? And what does decay mean? That means something happens to the nucleus. Okay. So unstable nuclei, when they decay, what you know, what do they become? Or what will happen? Not quite. Like, what's the point of decaying? Like, why do unstable nuclei decay? To become stable? Yeah, it's a very silly thing. But yeah, it's to become stable. The purpose of it is to become stable, right? Okay, but in doing so, it needs to release something, right? So it needs to like let off some stuff, right? So that's why we call it the alpha beta gamma decay, right? So if you haven't learned this yet, but you know later on you will, right? It's called the alpha, beta, and gamma decay, right? So in when you decay, right, you basically emit either one of these things here, that is, right? It's like releasing a particle at the same time is also releasing energy as well, right? So it's alpha particle or beta particle, right? And it's also at the same time releasing energy. So an unstable nuclei, right, will basically release energy by, sorry, unstable nuclei will decay, right? And in process of decay, it will become stable. How does it become stable? By releasing particles, alpha, beta, or gamma particles, and by releasing energy. Okay on this? Can? All right, good. So the next thing is you need to know the characteristics of decay. So if let's say someone asks you like, what's the property of nuclear decay? What are the two properties of nuclear decay? The two properties are, number one is spontaneous, number two is random. Okay. Now spontaneous, please memorize the definition now because I don't want to go through it again. Right? Spontaneous just means it cannot be affected by external factors. Right? So external factors it doesn't affect spontaneous decay, right? Which also means that you cannot trigger decay. You cannot put it on a frying pan and then heat it up and then make more of it decay. It won't do that. It will decay as and when it wants to, right? And when we talk about nuclear decay, is there anything to do with does it matter about which molecule is it in? Like like for example, if you have an unstable carbon, for example, carbon 14, right? Can I form carbon 14 dioxide? Like carbon 14, can I form carbon 14 dioxide? Can. It doesn't matter because nuclear properties does not affect its chemical properties. Do you understand that one more time? Nuclear properties does not affect the chemical properties, right? So this is not chemistry, yeah. I have to ensure that you remember this like over and over again. This is not chemistry, right? So this is about nuclear the stability of the nucleus, right? How about what was the isotope of hydrogen? I went through it last week. What are the isotopes of hydrogen? What isotopes do you get? What was one of the names of hydrogen isotopes? Deuterium and tritium, right? Okay. Could I have tritium dioxide? No, sorry, ditritium oxide. Sorry, ditritium oxide. What's ditritium oxide? Water. It's just heavy water. Hot water or heavy water? Hot water is different, right? Hot water is full of calcium carbonate, I believe. Is it? I'm sorry, I can't remember, but I think it's heavy water. But yeah, you could get tritium T2O. You could get T2O. That just means that it still behaves the same as the original element, but tritium is unstable. All right, tritium is unstable. Okay, anyway, so that's what spontaneous means. Spontaneous means that it will occur, right? No, because like on its own without any external factors, right? Random is there's no order of which the nuclei will decay, right? Please cancel this line. Sorry, this line is not for your level yet, right? So we don't have to worry about it. So there's no order. That's it. It cannot be predicted, right? No order in which the nuclei will decay, right? Cannot be predicted. Cannot predict. Okay, so make sure you understand that. Let's go on to the equations. Now, sorry, like I just realized I only have like 10 minutes left. But yeah, okay, so I'll go through these equations now. Can I? Yeah, so I just finish up these equations here. Okay, so what are the three kinds of decays do we have again? what are the three kinds of decay that we have again? Alpha, beta, gamma, right? So I'll tell you that this is alpha, this one here is beta, this one here please cancel out, and this one here is gamma, right? So this is not in your syllabus. In fact, this little bit here as well, just cancel this part out and just cancel this part out. Make sure your notes look like this. Make sure your notes look like this, okay? Right? These are not for you yet, right? This is for extra information, especially those who are taking physics Olympiads, right? Like, you know, you sort of like have to know this, but you know, for if you don't worry about this, okay? Right? So you got your alpha, you got your beta, you got your gamma. Let me tell you this, okay? Right? If you're very heavy, what's the fastest way of becoming stable? If an element, if an isotope is very heavy, that means it's very massive, got a very big nucleus. Okay, the fastest way is by alpha particle, right? The fastest way is alpha decay. So what alpha decay means is that the nucleus is so heavy is that it tries to stabilize itself by losing a chunk of it, right? And what chunk, right? By losing 4,2 helium. That means, right, when you go through alpha decay, right, you will lose 2 protons and 2 neutrons that are combined together. You're not losing 2 individual protons and 2 individual neutrons. You're losing just one like combined nucleus, which is a helium nucleus. Do you understand that? That's your alpha particle. This is your alpha particle. So whenever from now until the end of this year, whenever you hear alpha particle, you should understand that you're looking for a 4,2 helium nucleus. Helium nucleus, right? And I'm pretty strict on this. You have to remember that it's a nucleus. It's not what? Yeah, nucleus, not an atom. Okay, nucleus, not an atom. What's the difference between nucleus and atom? What's the difference between nucleus and atom? Atom has what? Nucleus don't have what? Yeah, atom has electrons, nucleus don't have electrons. So this is just legit just the nucleus itself only. Okay? So to help you understand, I want you to imagine that there is a pile of radioactive material, X here, like this, right? There's a whole pile of them like that. And then as it decays, right, it becomes V, which is undeniably more stable than X. Okay? So it'll decay and then give you a V, for example. So it decays, right? You get a V. It decays, you get a V. So the V is still within that pile, right? The V is still within this pile of radioactive material. But when it decays, right, it emits the alpha particle. So the alpha particle is emitted into, right, out of the pile of it. So it's emitted like that outwards. You understand that? Yeah? Does it make sense? I mean, it's hard to make sense of it, but yeah, this is what happens. So when your radioactive particle starts to decay, it will emit the alpha particle, it will shoot off like that, right? It will shoot off the alpha particle, right? And therefore, right, that's your, alpha decay. So now let's look at your beta decay then. Okay, your beta decay. So beta decay is when your when your isotope is not very heavy. So this one here is like, you know, too heavy, right? Too heavy. Okay, but for beta decay is when your elements are slightly smaller, but they are unstable also, right? Smaller and unstable, right? No matter what, it's unstable, right? So for beta decay, what's wrong with these elements? Either they have too many neutrons or too little neutrons. Okay, right? So for particles that go through beta decay, their problem is that they either have too many neutrons or too few neutrons, right? Either or, right? It's not that they're too heavy, right? Okay, so I will give you an example, carbon 14, right? I want you to think about carbon 14. Carbon 14. Do you think he's stable? He's not stable, right? He's not. Why is he not stable? Because he doesn't have the 1-to-1 ratio, right? Can he go through alpha decay? Do you think carbon 14 can go through alpha decay? Not likely. Why not likely? Because you have to release an entire 2 protons and 2 neutrons, right? Like carbon 14 is a very small molecule, a small isotope already to begin with, right? If you remove 2 and you remove 2, right, that's very unlikely. It's not energetically favorable for carbon 14 to release an alpha particle. So like I say again, alpha particles are generally for massive isotopes, right? Like for example, okay, example, uranium-235. Uranium-235, look at that, it's huge, right? Uranium is huge, right? Uranium-235, 235. Like in the nucleus, there's 235 protons and neutrons added up all together. This guy only has 14, right? You cut this guy off, this guy is just left with his skeleton already. Okay, right? Sticks and stones already. Okay, so you can't remove alpha. So, but no matter what, it's still unstable. It has what? Too many. What's wrong with carbon 14? You sure? Double check again. Double check again. Right? Difficult to do the math, right? On Sunday morning, 14 minus 6 is 8, right? So 8 neutrons, right? It's 8 neutrons. Like carbon 14 has 8 neutrons, right? Carbon 14 has 8 neutrons and 6 protons. Right? 8 neutrons and 6 protons, correct? So it doesn't fulfill the 1-to-1 ratio. So what's wrong with it again? Too many neutrons, right? Okay, here's the deal. It's gonna sound damn strange. It's gonna sound damn weird. It sounds like I made this up, right? But it's not. I didn't. I swear I didn't make it up. Right? One of the neutrons will turn into a proton. I'm not shitting you, okay? Right? One of the neutrons will become a proton in order to make it stable. But does it work though? Like, does it make sense for it to do that? Like, look at carbon 14. What's wrong with it again? Too many, too many neutrons. Too many neutrons, right? The 1-to-1 ratio is better, right? So, since it's unstable, it needs to decay. It cannot release alpha particle because it's too much, right? It's too big a chunk of it. So one of its neutrons will just conveniently become a proton. Okay? Okay? This conversion will emit an electron. So the proton will come with an electron, charge is conserved, right, which is fine, but this is your beta particle. The electron is your beta particle. Right? But specifically, not all electrons are beta particles. Beta particles are high Ke electrons. High energy electrons. Okay, very, very specific. They must be super high energy. In fact, they're so high energy that they're traveling around the 99% the speed of light. Yeah, that's how high it is. Okay, so that's a very high energy beta particle there, right? So you got your element here, right, at first, and then one of the neutrons will become a proton, and then the beta particle is emitted at the same time. You understand this? Yeah, it's weird. So imagine that you have a pile of like elements here, right, and then it becomes a Y, right, and it emits a beta particle, right, out when it does that beta particle thing. Notice how the nucleon number doesn't change. Like the total number of protons and neutrons stay the same. Does it make sense to you? If one of the neutrons becomes a proton, then the nucleon number stays the same. You get it? Yeah. Right, there's one. Okay, so there's only 3 kinds of decay that you learn. Alpha, beta, and the last one is gamma. Okay, look at gamma. Look at the gamma equation, right? Nothing happens to the nucleus. The nucleus stays exactly the same. It's just kind of like leftover energy, like extra energy. So we say that this nucleus, right, is excited. Is an excited state. Excited state. So if it's to decay, it will decay. It will decay into the stable state, which is non-excited state, right? And in doing so, it emits a gamma photon. This is gamma radiation. Gamma radiation. Okay, we're good. Do you notice there's one thing that I didn't touch on? I missed out on. What happens if you have too many protons? It means you have too few neutrons. Huh? That's also beta, but this is a bit different. This is called beta plus. This is the beta plus decay, right? So you know this part I asked you to cancel out because it's not technically in syllabus, but I did go through with you. Too heavy alpha, right? Too many neutrons beta, right? Gamma, nothing's wrong with the nucleus, it's just too excited, it got too much energy, so it releases energy, it's gamma radiation, right? So the problem is what happens when you have too many protons, right? So if you think about this, it makes sense. Too many protons, one of the proton will become a neutron, and that solves the problem, right? You got one more extra neutron, but you have one less proton. Right, so it helps you to stabilize the nucleus, right? Correct, but this is not in syllabus because it releases a particle that's called beta plus. It's called a positron. I know, I'm not making this shit up. Okay, this is a positron, right? And if you look at the name, yes, it's a positive electron, which is considered as an anti-particle, antimatter, but that's not in your syllabus. If you want to go read up more about this, you can go read up more because I know some of you are interested in this kind of shit, right? So if you want, this is called antimatter, right? Antimatter. And this is not sci-fi. You go to any hospital these days, right? They have a positron lab in the hospital, right? Positrons are used to detect cancer. Yeah, right. But there's none of your business in this syllabus. Okay, so this is just general knowledge. But for now, you just need to know this. Okay, next week I'll continue. All right, I'm gonna stop here now. Those online, thanks very much. I have to kind of like ask you to log off. Right, sorry about that. Yeah, keep me updated on WhatsApp, please. Thank you, Kyrie.